Welcome to Chapter 3, where we explore element property databases and featureizers. The quality of composition-based features depends on the elemental property data you use. We'll compare 3 major data sources and learn to use multiple mapminer featureizers, including creating custom featureizers for domain-specific applications. By the end of this chapter, you'll understand the differences between Mendeleev, PyMatchen, and mapminer data sources and know when to use each. You'll gain practical skills in implementing element property, stoichiometry, and oxidation states featureizers. You'll also learn to design custom featureizers and integrate multiple data sources for comprehensive feature sets. Element property data comes from various sources with different characteristics. Mendeleev provides comprehensive experimental values. PyMatchen focuses on materials science applications with DFT-derived properties. Mapminer integrates multiple data sources specifically for machine learning. Understanding these differences helps you choose the right source for your application. The Mendeleev library provides data for all elements with many properties each. Data comes from reliable experimental sources like NIST and the CRC handbook. It's updated regularly. The advantage is high reliability with clear provenance. The limitation is that it doesn't include DFT-calculated values, and some properties are missing for synthetic elements. PyMatchen's element class is designed for materials science applications. It integrates with Materials Project, provides both experimental and DFT-derived properties, and handles oxidation states and ionic radii. It's the foundation library underlying mapminer. Use PyMatchen when you need material-specific properties like ionic radii for different oxidation states or electronic structure data. Mapminer, developed by the Hacking Materials team at Berkeley Lab, is specifically designed for machine learning on materials. It provides multiple presets including MagPy, Deml, Mapminer, Matcholr-L, and Magnet-L. All featureizers are scikit-learn compatible, producing data frames ready for ML pipelines. The workflow goes directly from composition strings to feature-ready data. Let's compare the 3 sources. Mendeleev has the highest reliability with pure experimental values, best for precision applications. PyMatchen combines experimental and DFT data with crystal structure focus, best for materials simulation integration. Mapminer provides ML-ready outputs with multiple presets, best for machine learning workflows. Choose based on your primary use case. This code compares iron properties across all 3 databases. We retrieve atomic mass, atomic radius, and electronegativity from Mendeleev, PyMatchen, and Mapminer. The output table shows slight variations between sources. Most values agree closely, but differences can occur due to measurement methods or DFT approximations. Always be aware of your data source. Mapminer provides multiple featureizer classes beyond element property. We have stoichiometry for composition ratio features, oxidation states for charge state analysis, ion property for ionic character descriptors, and Yang solid solution for high-entropy alloy design. Each serves different applications and can be combined for comprehensive feature sets. Element property is the primary featureizer class. The From Preset method provides access to multiple elemental property databases. Available presets include MagPy, Deml, Mapminer, Matcholr-L, and Magnet-L. Each preset has different strengths and feature counts, ranging from around 100 to over 100 features. The MagPy preset, developed by Ward in 2016, is the most widely used and benchmarked. It provides over 100 features from elemental properties times statistics. It achieved excellent predictive performance on OQMD formation energy. Feature names follow the pattern MagPy data followed by statistic and property, like MagPy data mean atomic radius. The Deml preset, from Deml and colleagues in 2016, explicitly considers oxidation states. It produces about 60 features and is particularly strong for oxides and ionic compounds where oxidation state matters. If you're working with battery materials, ceramics, or other ionic systems, DEML may outperform MAGPIE despite having fewer features. The Magnet-L preset, from Chen and colleagues in 2019, supplies learned elemental embeddings taken from a trained magnet model. Matchaler-L, from Tishatoyan in 2019, uses natural language processing on about 3.3 million materials science abstracts to extract element embeddings. This captures implicit knowledge from the literature that might not be in explicit property databases. The stoichiometry featurizer provides composition-level features without elemental properties. It calculates p-norms of the atomic fractions. The 0 norm gives the number of element types, while the 2, 3, 5, 7, and 10 norms measure how evenly the composition is spread. With only 6 or 7 features, it's lightweight but captures important compositional information. It complements element property nicely by adding stoichiometric structure. The oxidation states featurizer predicts likely oxidation states for each element and calculates statistics. It's particularly important for ionic materials, battery electrodes, and catalysts where charge state affects properties. Note that the composition must carry oxidation states first. Charge balance feasibility is a separate check. For example, Pymatgen's oxy state guesses. The Meridig featurizer, from Meridig and colleagues in 2014, provides the descriptor set from that formation energy study. 103 element fraction columns plus 16 curated descriptors. It gives an explicit element fraction representation that complements MAGPIE's statistical aggregation. Sometimes simpler models with fewer features perform just as well. The Yang solid solution featurizer calculates 2 parameters for predicting solid solution formation in high-entropy alloys: omega, which balances mixing entropy against mixing enthalpy, and delta, which measures atomic size mismatch. Together, they predict whether elements will form a stable solid solution or phase separate. It's specifically designed for HEA design applications. A single featurizer may not capture all relevant information. Combining multiple featurizers creates a more comprehensive feature set. The multiple featurizer class concatenates outputs from several featurizers. You might combine MAGPIE for elemental properties, stoichiometry for composition structure, and oxidation states for charge information. Multiple featurizer takes a list of featurizer objects and applies all of them to each composition. Import it from mapminer.featurizers.base. Pass a list of initialized featurizers to the constructor. The output data frame contains columns from all featurizers concatenated. Total dimensions equal the sum of individual featurizer dimensions. Here's a complete example combining 3 featurizers. Create element property with MAGPIE preset, stoichiometry, and oxidation states. Wrap them in multiple featurizer. Apply to your composition data frame. The result has about 140 columns covering elemental, stoichiometric, and charge properties. Sometimes you need domain-specific features not available in standard presets. Custom featurizers let you add properties like element cost, crustal abundance, toxicity, or any other per-element data relevant to your application. By inheriting from base featurizer, you create compatible components that integrate with mapminer pipelines. To create a custom featurizer, inherit from base featurizer and implement required methods. The featurize method takes a composition and returns a list of feature values. The feature labels method returns feature names. Optional methods include citations for references and implementors for credits. Following this interface ensures compatibility with multiple featurizer and Sklern pipelines. Here's an element cost featurizer example. Define a dictionary mapping elements to their market prices per kilogram. In the featurize method, extract element fractions and calculate weighted mean cost, maximum cost element, and cost range. This helps in materials selection considering economics. Return the values as a list matching your feature labels. An element rarity featurizer uses crustal abundance data. Invert abundance to get rarity. Rare elements have high rarity scores. Calculate mean rarity, max rarity indicating supply chain risk, and rarity variance. This helps design sustainable materials avoiding critical elements. Similar patterns work for toxicity, recyclability, or any per-element property. Raw features need preprocessing before machine learning. Standardization ensures all features contribute equally. Missing values must be handled appropriately. Feature selection can reduce dimensionality while preserving predictive power. These preprocessing steps are critical for model performance and should be part of your pipeline. Standard scaler transforms features to zero mean and unit variance, essential for many algorithms. Min-max scaler maps values to 0 to 1 range, useful when you need bounded values. Robust scaler uses median and quartiles, resisting outliers. Always standardize after train test split using only training data statistics to avoid data leakage. Some elements have missing property values, especially rare earths and synthetic elements. Options include dropping rows with any missing values using dropna, filling with column mean using fillna, or using Sklern's simple imputer for more sophisticated strategies. Check which elements cause missing values and consider whether your application needs those elements. MAGPIE's many features may include redundant information. Variance threshold removes near-constant features. Select K-best keeps the top K features by statistical test. Recursive feature elimination iteratively removes least important features. In practice, a much smaller subset often achieves similar performance to the full set. Fewer features means faster training and better interpretability. Let's summarize Chapter 3. We compared 3 data sources: Mendeleev for experimental values, PyMetchin for materials science, and MapMiner for ML workflows. We explored multiple featurizer types: element property, stoichiometry, oxidation states, and specialized options. We learned to combine featurizers with multiple featurizer and create custom featurizers. Finally, we covered preprocessing essentials. In Chapter 4, we'll integrate composition features with machine learning models. We'll build scikit-learn pipelines for end-to-end workflows. We'll compare models including random forest, XGBoost, and neural networks. We'll optimize hyperparameters using Optuna. Finally, we'll interpret predictions using SHAP values for physically meaningful insights.